Hi, this is Mr. Heineman from Evergreen High School. This is for my Algebra 1 classes. This is Standard 3.1, Creating Linear Equations. So in Unit 3 here, we've broken up the content into kind of separate pieces. One of those is linear equations, the other one is linear inequalities. The main reason for that is that we have standards that relate to those individually rather than standards that relate to both of them in one. So we're going to start by looking at linear equations. And linear equations, the reason why they're linear is because they have a constant rate of change. And that's true of all linear equations as well as linear inequalities. They will have a constant rate of change, which is what makes them linear. And so we have multiple ways that we represent those linear equations. We use, of course, equations, which are in symbols. We graph them. We use tables, which is numerical. And then we use stories, which is words that describe a situation that has a constant rate of change. And that's the main thing that we need to pay attention to, is that constant rate of change. There will be other things that we'll talk about related to specific forms of linear equations. But the main thing to remember is that linear equations have a constant rate of change. So when it comes to solutions of linear equations, previously when we solved equations with one variable, we found a value that made the equation true. But now that we have linear equations and we're going to have two variables, those two variables have to both have a value that'll make a linear equation true. So any solution is going to be a point that makes the equation true. And when we say a point, we mean an ordered pair on a graph, an x and a y coordinate. All of those solutions, those points for a single equation, will appear in the graph on a single line. And I know people like to call it a straight line. Mathematically, when we say line, we mean a straight line. So that's the terminology I'm always going to use, is that when we say line, we mean straight line. I don't mean anything other than a curved line. And I know that in other subjects or other places in the world, when we say line, we mean something that you draw or whatever. In math, a line is straight. That's just how it is. And so I'm only going to use the word line. That's why we call them linear equations, because the solutions to a linear equation always form a line. So just like we did with equations, we can use or we can verify that something's a solution using one of the representations. In this case, because we now have more representations of linear equations, we need to practice with all of them, at least with 3 of the 4. So when it comes to tables, the point is the point 3, 4 a solution? Well, it's either in the table or it's not. And I'm going to look and I see, oh, here it is. It's right here. And I would look where the x value is the same. And if I had a different y value, I could tell you that solution must not be there, because in a linear equation, if the x value is 3 and the y value is not 4, then it must not be a solution. And in this case it is, yes, because the point appeared in the table. And it's really that simple. It's in the table, therefore it's part of the linear equation or linear relationship, and therefore we can say it must be a solution. Okay, so that's solving using tables. On a graph, as I said, a point is going to lie on this line. All of the points on this line are the solutions to a particular linear equation. In this case, this line is different from that table. Here's the y. Here's the x value of 3, and we see 3, 4 is right here, and it's on the line. So this is also a solution of this one, because the point is on the line. And it really is that simple. Right? If the graph of a linear equation, the set of all solutions is the line, then if it's on the line, it must be a solution. And if it's not on the line, it's not. Okay? In the equation, we actually have to test the point by substituting. And sometimes it can be, well, if you go too fast, you might plug the wrong value into the wrong spot. So make sure you're plugging in y for y and x for x. And then we're going to see if this equation is true. It's 12, 4 equals 2. That's not true, so this is not a solution to this linear equation because when I substituted the point in, substituted the point into the equation, it wasn't true. So solutions will make linear equations true. They'll appear on lines of graphs, or they'll be somewhere in the table. So when it comes to linear equations, they come in two different forms. The first one that we just saw was called slope-intercept form, and it's named slope-intercept form because you can see the slope and the intercept just by looking at it. And we have two different equations here, but they're both basically the same. They have this red box by x, and they have a blue box separate from x. It's just that whether the red box and x come first or whether the blue box comes first. In either case, we can identify what the slope and intercept are by looking at either of the boxes. So the two blue boxes that are separate from x, those represent the y-intercept. That's the value that the line is going to be at when the line crosses the y-axis on the graph. It's also where x is equal to 0, because that's on the y-axis. All x values are 0 for all points. Some people think of it as like a starting point, and when it comes to stories, that's what we'll use as our y-intercept is always going to be the starting point. Okay, that means that this value, whatever it is, next to x, is the slope. And so looking at any linear equation in slope-intercept form, we can quickly identify slope and intercept by knowing that slope is always next to x and y-intercept is the other number that's not next to x. The other form that we have is called standard form. And standard form obviously looks different. X and y are both on the same side, and there's 3 spots for numbers. There's this one, which is a rate of change, like slope, but we don't call it slope because if we converted this to slope-intercept form, which we could, like we would with rearranging formulas, the actual slope would be a combination of these 2 rates of change. So they're both rates of change. We could say 1 and 2 just to differentiate between the two of them. And then this is some total. And that's how it's going to be presented in word problems and in stories, is that there'll be a rate of change for x, a rate of change for y, and then a total. And like I said, the total isn't necessarily going to be the y-intercept. In fact, most times it's not the y-intercept. The y-intercept we can find by plugging in 0 for x and then solving the resulting equation for y. And we can do the same thing for the x-intercept, and we'll talk more about that when we graph standard form equations. But know that a standard form equation looks like this. There are 2 rates of change plus a total. So when we graph slope-intercept equations, what we can do is we can fill in this table with all of the y values for these corresponding x values. And one way that makes the table go real quick is to use the structure of this expression and the structure of a slope-intercept form equation to our benefit. So we know that a slope-intercept form equation has a slope and intercept. Slope is here, x2, x. That means that this, with the sign, is the y-intercept. And that means that in my table, of course, the y-intercept is going to be physically on the graph. It will be where I cross the x-axis, or the y-axis, which is right there. But then also, in the table, I'm going to put it right here where x is 0, because that's the x-coordinate of the y-intercept is always going to be 0. Then I can use my slope to figure out the rest of the table really quickly, because as I move down, I can add my slope, in this case 3. So when I just add, I'm going to keep going and add 3 each time, because I know it's a constant rate of change. It's always going to be 3 as I go down the table. And then if I go up, I'm going the opposite of down, so that I'm going to do the opposite operation, and I'm going to subtract. And then I just got to remember, when I do subtract, I can, when I go into negatives, of course, when I start subtracting, it's like adding 2 negatives, and so I'm going further negative. So now I look, and each of these adds 3 as I go down from the top to the bottom. They're 3 apart, which is what a linear relationship is. So then, I've already graphed this one, so what I can do to graph is I can first graph or plot my y-intercept, and then I can also plot a second point using my slope, which is easy enough to do because I can go from here and I go up 3 and then to the right 1. And that forms this little triangle when I connect these, because what I would do is I would use a straight edge and then I would connect the dots like this with my line. And now you can see the triangle, and this constant rate of change makes it easy to know where all the points are going to be. So, right, 2, 10, and if my set of coordinates, or my set of axes, I should say, had more space, we would see all the other points. And we always continue on in both directions forever. That line goes in both directions for as long as you can. We're not limited by just what we see. We're just seeing one little piece of it. So what's nice about graphing slope-intercept form equations is that you kind of already have a couple of points really given to you, although you do have to kind of find the second one. But that y-intercept and then the 1 point are easy enough to find, because when you find, or when you just use the slope, you start at the y-intercept, you go up your slope amount into the right one. With standard form equations, it's not so easy, but it's still not too bad to graph, because what we're going to do is we're going to find both intercepts. And to find both intercepts, what we do is we plug in 0 for x to find the y-intercept, and we plug in 0 for y to find the x-intercept. And so what that effectively does, when I plug in 0 for x, well, 2 times 0 is 0. That's going to get rid of this x term. It's going to leave me with this equation. So when x is 0, I need to figure out what y is. Well, that's just a one-step equation. I'm going to divide by 5. So in this case, y is 4. So there's my y-intercept. I can plot that right here on the graph. And then I do the same thing for x. I plug in 0 for y, which effectively gets rid of that term, and then 2x equals 20. Divide by 2, and x equals 10. And so then I can plot that point as well. And then when it comes to graphing equations, or linear equations, once I have 2 points, I can graph the line. And I use a straight edge to do that so that my line is nice and straight. So the basics of graphing any linear equation, whether it's in slope-intercept form or standard form, are to find 2 points and then connect those 2 points with a line, and of course go through both points and continue on. Um, the way we find the 2 points depends on the form we have. If we have linear or slope-intercept form, then we have an intercept. We have the y-intercept, so we take the y-intercept and plot it, and then we use the slope to find a second point. So we go up our slope amount and to the right one, plot a point. For standard form, we substitute 0 for each of the variables one at a time. So we do x and y. So I plug in 0 for x, and then I solve that equation for y. That's my y-intercept. And then when I do the same thing for x, I find my x-intercept, and then I connect the dots with my line. So when I write a linear equation from something, when I'm writing linear equations, first of all, we should know we're always going to write them in slope-intercept form. It's just easier to do, and we're usually given all the information we need to do that. So when I look over here, I'm looking at a graph now. Well, then my job is to find, right, I know I'm going to have y equals, and then I'm going to have some slope, x to x, and then some intercept. And I'm not going to put a sign for that yet because it might be positive, it might be negative. It all depends on my situation. So when I'm writing the equations, I'm going to identify what the intercept is. In this case, the intercept is positive 20. So I know my intercept here is going to be positive 20. And then I check my slope by moving over 1 and seeing how far up we went. And so here's my next point. So this distance divided by this distance. Well, I know this is 1, so this will be my slope. And I see it goes up from 20 to 24. So this slope is 4. So my equation is 4x plus 20. So y equals 4x plus 20 is this. And I know that because both of them have a y-intercept of 20, and both of them have a slope of positive 4. So when it comes to writing equations from tables, now I'm using numerical information to figure out what the slope and intercept are. So the slope, of course, is going to be where x is 0. And if I say this is going to be x, this will be y, because that makes sense. If I work so many hours, I'm going to have a total amount of money. My y-intercept, therefore, is 205. So when starting writing my equation, I know I'm going to have some x value plus 205, or some slope in front of x. And then I need to figure out the slope. Well, if I know this is plus 1 here, so if I figure out how much plus here is, then I'll figure out the slope. And because that tells me how much is being added each time. So I go 216 minus 205. And it turns out that is 11. And if I check, I'm hoping that just do a real quick check to make sure that this is also plus 11, and it is, and plus 11, plus 11. So you just want to make sure that it's a constant rate of change, because it should be. And again, these are both true because we can see that the rate of change is always plus 11, and so on. And we started at 205. So for every 1 we move over, we're adding 11 of vertical movement. When it comes to writing equations from stories, now we can actually potentially write them in either slope-intercept form or in standard form, depending on what information we're given. And so for slope-intercept form, of course, we're going to be looking for a slope and an intercept. For standard form, we're going to be looking for 2 rates of change and some sort of total. It doesn't always mean that 3 numbers is going to tell me that it is a standard form equation. Those 3 have to be the right type of numbers. So when I look at this one, it says a Lunders family bought sandwiches for $5 or for $4 and salads for $5. And those 2 values seem like they are rates of change because they were saying sandwiches are $4. So that's $4 per sandwich and $5 per salad. And when they spent $40, that sounds to me like it's a total. So I think this is a standard form equation. In this case, X is going to be sandwiches, just for the sake of argument, and Y will be salads. And that way we know what we're representing. So when I write my equation now, my rate of change goes ahead of X, at least the rate of change for X goes ahead of X, and the same thing for Y, and then the total is on the other side. And that's all there is to it, to writing equations from stories. It's just a matter of finding the right information that you need that will give you whatever equation that you that goes with that. Just remember that not all numbers are necessarily going to be used in your equation. You need to make sure you're reading carefully to check and see if the numbers in your story are actual ones you want to use in your equation. So sometimes we're asked to write equations for a situation where we're given what seems like not enough information. And so it's still up to us to figure it out, and we can figure it out as long as we have the right kind of information. So when we look at this problem and we see that Daviana is saving for college, and by the 4th month she had $280, and in the 9th month she had $490, so, or $390. So our job is to figure out what did she have to begin with before she started saving, because then we'll be able to figure out where she started, and then we can write an equation based on it where we start at y equals, and we have a slope and an intercept. So we're also going to have to figure out how much she's saving each month, which is what our slope represents. So one way we can do that is to create a table and then fill in the table. And we know that our y-intercept is going to be where x is 0, and we don't know what it is right now, but we can figure it out once we know how much she's saving each month. And so when we count down here to the 4th month, it's $280. And then in the 9th month, she has $390. And so our goal is to figure out how much has she been saving each month. We know that in 5 months, she saved a total of $110. Which means we can figure out if she saves the same amount each month, the amount she saves each month is going to be whatever 110 divided by 5 is. And so 110 divided by 5 ends up being 22. So she's saving $22 each month. So we could actually fill in the gaps here by adding $22 each month. So $22 here is $302, $324, $346, $368, and then plus 22 will give me $390. But that also means that if I go backwards, I can subtract 22 because I moved backwards 1 month. And so when I go 280 minus 22, that is 258, and then minus 22 again would be 236, minus 22 again, 214, and then minus 22 one more time would be 192. So she started with 192 and then added 22 each month. So when I write my equation, y equals, I can say she started at 192, and then each month we added $22, and x represents the months. So making sure that this is the number of months, and then this is total saved. And that's in dollars. So we can write an equation when when it doesn't seem like we have enough information. We just need to figure out what the rate of change is between the 2 points that we do have, because essentially these are 2 points that are part of this line. It was just our job to figure out what's the difference between these two, divide it by the difference between those two, and then we get our slope. And then we can use the slope to go back and find the y-intercept. So that's it for linear equations. We'll continue with linear inequalities.